Welcome students. In this video we are going to talk about asymptotic behavior of the solution to the linear system. This is the third part essentially. Okay. So we talked about what happens when we have a constant coefficient equation, right? So in this part we are consider this problem. Consider the homogeneous problem. The problem x prime equals to at times x. It is okay. Simple equation here. But here this a is variable, right? It depends on t, where a is given by aij. Let's just call it aij. Okay, n cross n, and has continuous entries. Clear? Continuous entries, right? So now let's look at what is the behavior of the solution. So now the question is this question: what is the behavior? It's the behavior of the solutions of one as t tends to infinity. That is the question. Yeah, very simple question. Yes. Now here what we will do is this: we will see that if we want to study this sort of thing, we need to involve the eigenvalues, okay, of some particular matrix. So what we are going to do is this. See, first of all, let's look at this theorem. We start with this theorem. Theorem 1. Yes. So let the matrix A of t is continuous on 0 infinity. Yeah, this you have always assumed, but let's just write it in 0 infinity, and mx, clear, and m of x be the largest eigenvalue, okay, eigenvalue of the matrix A transpose t plus A of t. So basically I am looking at the matrix AT plus A transpose t, and we are assuming that this is m of t, this is the largest eigenvalue of that matrix. Clear? Of course, you see A depends on t, right? So the eigenvalues will also depend on t. We are assuming mt is the largest eigenvalue. Clear? Then every solution of one tends to 0 as t tends to infinity. Clear? So basically every solution, what I am saying is this: they are not only bounded, it tends to 0, okay, as t tends to infinity, provided, what is the relation? Provided 0 to infinity. This doesn't have to be 0, it can be from any x naught, t naught, doesn't matter. So basically what it is saying is the tail part, this should be minus infinity, okay, the integrability. Okay, now let's look at it. What is essentially what we are trying to do here. So the proof. So let x of t solves 1, right? Solves 1. Clear? Then x of t square, how can you write it? We can write it as x transpose of t, x of t, right? See, let's say that for 2 cross 2, let's just do it for 2 cross 2. X of t is nothing but x1 of t, x2 of t, right? So the square if you take, okay, so and the modulus of square, that will be x1 square plus x2 square. Okay, now you can break, you see, x1 x2 and x1 x2. Okay, if you just do that, then you can see that if you multiply it, it is going to be this thing. Okay, so this is what we wrote. Sorry, this square, the root is not there. Root is not there because the square is part is there, right? So you can see that this is happening. Okay, so this is true. Sorry. Now, therefore, d dt of xt squared, what happens to this? This is nothing but x transpose t, x prime of t plus x transpose t, the prime of that, times x of t. Is this okay? And then that will imply that x transpose of t, you see, x prime of t is nothing but 80 times x, right? So it is 80 times x of t plus this part, x transpose of t prime, right? So this is x transpose of t, a transpose of t, right? And then x of t. Clear? Okay. So now this can be written as x transpose of t, and if you take this part common, it is at plus a transpose of t times x of t. This is okay. Now you see this matrix, one beautiful thing about at plus a transpose t is it is symmetric. So since a transpose t plus a transpose, sorry, plus at is symmetric, and what is given, and m of t is given to be the largest eigenvalue, right? Is the largest eigenvalue. Eigenvalue of this matrix, right? A plus a transpose. Okay, so what can we say? So therefore x transpose of t, sorry, transpose a transpose plus a at plus a transpose of t, this times x of t is gets dominated by m of t times x of t square of that. Yeah, this is true. Therefore, since this is eigenvalue that is going to happen, right? Okay, so for t greater than equal 0, what do we have? 0 is dominated by mod xt square. Okay, equals to is when xt equals to 0, and if xt is not 0, then it is greater than equal 0, greater than 0 strictly. Yeah? And then these will be dominated by x at the point t naught square plus 0 to t m of t x of t square dt, right? I'm just replacing this thing. See xt square, okay, xt square, this part, okay, xt square, okay, I am just writing it like xt, dt of xt square is this, right? Okay, so xt square I will just write it as integral. If you take the integral on both sides, then xt square minus xt naught square is dominated by 0 to t mt xt square dt, right? I will just take the derivative on both sides, okay? ddt of this is that, then fundamental theorem of calculus I will use. Now therefore, now you see this is in the Gronwell form, right? xt, and this is, sorry, I should write it like, one second, let me change the variable a little bit. I should write it at ds. Yeah, this is okay because the integral is from 0 to t, right? Okay, so I have to change the variable a little bit. I'm sorry about this. Variable needs to be changed. So ms. I hope this is fine here. Now by Gronwall inequality, we have that norm of xt square gets dominated by norm of x0 square. What is t naught? Let's just put it as 0. Exponential 0 to t ms ds. Is this okay? Now therefore, if exponential 0 to t ms ds, okay, see, the thing is, if the tail part of this 0 to infinity mt dt, if that part is basically minus infinity, right? So this goes to 0 in that case, this goes to 0, yes, and then xt will also go to 0, right? Because this is basically bounded, x at the point 0 is some fixed number. Okay, so if this is going to 0, then xt goes to 0. So basically, you don't have to do anything. This, the result concludes by the given condition. Yeah. Okay. So see here, you don't have to be 0 to infinity. It can be large enough t. So basically, from some t naught to infinity also for large enough t naught. Doesn't matter, huh? You don't have to put any condition on this lower bound. So basically, what it is saying is after some time the integral should be, because m is continuous integral. Okay. So after some time it has to, the integral has to be minus infinity. That's all. Okay. I hope this is clear. Very, very simple. I mean, it's not a very difficult theorem to prove actually. Okay. Now let's say that, now a small remark let us put on a remark. If let's say, let me put it this way, ms ds, if we write it, if this condition, this is important, right? This condition guaranteed that xt goes to 0. Now if we are replacing this condition, mt dt is finite. Yes, it doesn't have to be minus infinity, but it's basically finite. If you have that, then what can you say? From exactly this thing, you see, you can say that if this is finite, then exponential that part is going to be finite. So basically, all solutions x of t remains bounded. Right? That's what it is saying. All solutions x of t remains bounded as x tends to infinity, t tends to infinity, as t tends to infinity. Is this okay? Right? See, if this is bounded, exponential of that function is going to be bounded, and then x of t is going to be bounded. So basically, this is a very, very simple, remark from this part here. Okay. We can also say more. Yes, we can also say more that this is a. Okay. Right. Now b. This remark, yes, I am doing it. I want you to do it yourself. Please do this part. Okay. So the thing is, let's say that if you see capital M of, where is it, yeah, capital M of t is the largest eigenvalue, right? If you have small m of t be the smallest eigenvalue, let's say be the smallest eigenvalue of a t plus a transpose of t. Yes, if this is the case, then a beautiful thing happens, then every solution of 1, okay, is unbounded as t tends to infinity, clear, provided lim sup, okay, as t tends to infinity, that is t m of s ds, this should go to infinity. Is this okay? See, how do you, so this part I want you to check it yourself, check. Okay, so this is a condition under which all solutions are unbounded. How do you prove something like this? Exactly the same proof which we did here. You see here, since capital M is the largest upper bound, we got this. So in this case, you will get, here it will change, you will greater than equals small m times x naught xt square, and then you do exact the same thing, the same sort of analysis you have to do. Okay, and once you do it, you can actually show that if this limit supremum, where is it, limit supremum is infinity, then we have also it's not unbounded. Okay, you have to check it yourself, but exactly the same sort of proof works, so you do not have to worry about that particular point. Okay, so let's look at some examples now. Example 1, let's say. So let's say AT is a matrix given by 1 by 1 plus t square, and this is t square, right? And then minus t square and minus 1. Is this okay? Therefore, let's say this is A of t, AT plus A transpose of t, what is it? It is 1 plus 1, okay? So 2 by 1 plus t square, and then t square minus t square, so this is going to be 0. Again t square minus t square, this is going to be 0, and this is minus 1 minus 1 minus 2, right? So this is what we are going to get, clear? And therefore, what is m of x? M of x, define m of x to be the maximum, you take all the eigenvalues, it is the maximum of that, right? Okay, so so for this, the eigenvalues are 2 by 1 plus, see this is like a diagonal matrix, right? The eigenvalues are 2 by 1 plus t square and minus 2. Okay, so what is the maximum here? It is 2 by 1 plus t square. I hope this is clear. See, this is the diagonal matrix, right? The eigenvalues are basically the diagonal elements, okay? And between minus 2 and 2 by 1 plus t square, maximum is 2 by 1 plus t square. So m of x is 2 by 1 plus t square. That's just definition, right? And 0 to infinity, m of s ds, what happens to that? It is 0 to infinity, okay, 2 by 1 plus s square ds. This is okay, right? Now you can calculate this thing, okay, and please do this part you have to check it yourself. It's not of course this is very easy, no? Please do that. So if you check that, this is going to be 2, which is bounded. Okay, so what can you say if you can see that this is going to be, what can you say? You can say, you use this first part of the remark, if this integral up till infinity mt dt is finite, then all solutions remain bounded as t tends to infinity. Is this clear? Okay, so therefore all solutions of x prime equals to at times x, clear, remains bounded as t tends to infinity. Is this okay? Very simple. Okay, so this is the first example. Let's do another example. Okay, example 2. So you see, let's say at is minus 1 by 1 plus t. Okay, and this part is 1 plus t square. The second part is minus 1 plus t, and the third part is minus 2. Is this okay? So therefore, let's look at what is a of t plus a transpose of t. So this is nothing but, of course, again, a plus a transpose, a I plus a I, so it is 2 by 1 plus t. Okay, this and this, let's write it as t square. Huh? So it get cancelled out and becomes 0. So we are just making our life easier, basically. Yes. And again, this term is going to be 0, and this is minus 2 minus 2 minus 4, right? Okay. So now we have to calculate that what is m of x. And what is m of x? Sorry, m of t. See, out of these two, it is very clear that minus 2 by 1 plus t is the 1 plus t. The maximum is given by this, right? M of t. Okay. So again, if you are not convinced, check. This is trivial, right? Of course, you can see that. Okay. So since this is the case, therefore, what do you have? Therefore, 0 to infinity m of t dt, if you calculate that part, here, that will be nothing but 0 to infinity minus 2 by 1 plus t dt, right? And that is going to be minus infinity if you calculate it. Yeah. Therefore, all solutions by the theorem, all solutions of the differential system x prime equals to at times x goes to 0 as t tends to infinity. Okay, so very simple. Yes, see, you just have to calculate what's the eigenvalue, and then you are more or less done. Okay, so you don't have to worry about any other thing, to be very frank with you. Okay, so now what we are going to do is basically we are going to look at a different kind of problem. Okay, so you see, up till now we have looked at this problem, x prime equals to ax. Okay, and then what happens? This is the purely homogeneous case, and then we looked at a plus bt. Okay, a part of system x. Here, then we looked at this problem, x prime equals to at times, sorry, ax, the homogeneous problem, right? Ax plus b of t. Okay, now this video we talked about this problem, at times x. Okay, now what is the most natural thing to do here? Now we will talk about again the part of system. So x prime equals to at plus bt, okay, times x, and then what happens? Okay, let's just do that part. Clear? Once we do it, and then we'll look at some other important theorems. Okay, so first of all, we start with a theorem. Okay, so theorem. This is theorem 2. Theorem 2. Okay, so let all solutions all solutions of the system x prime equals to 80 times x, clear, are bounded in 0 infinity. Okay, so in the first part we have seen, right, that when are all solutions bounded, uh, when integral mt dt is finite, right? That's what we have seen. We just looked at it. Okay, so this is the assumption. Okay, now are bounded in infinity, and let this is the condition which I am assuming. Infinity norm of bt dt is finite. Okay, this is what we are assuming. If this happens, then all solutions of this equation, x prime t equals to at plus bt times x, the part of system, yes, okay, are bounded in 0 infinity, provided limit infimum the trace of a matrix A of T. Okay, this is a little different, and this is a very, very important theorem. Please remember, trace of AT greater than minus infinity, or if trace of AT equals to 0. Clear? Very important. So here what it is saying is this: if you have a part of system, you want to see whether all solutions of the part of systems are bounded or not. What you have to do is you just find out if all solutions of the homogeneous systems are bounded, and integral up till infinity. So basically up to norm of bt dt, you take up till infinity, that is finite. Okay, yeah. So before I do that, let me do a small remark in case you do not understand. See why I am not putting a lower bound here. See, let's say if I put 0 to infinity norm bt dt is finite. Okay, this saying this and saying this is, and if I am not putting anything, so basically it says that you can start from anywhere. So let's say I can start from any t naught to infinity, norm of bt dt is finite. Okay, see in 0 t naught, okay, norm of bt this is continuous function, right? Is continuous. So basically what happens is that interval is always bounded. Okay, so if you're taking the integral on a finite set, so basically that will imply that integral between 0 to t naught norm of bt dt, there is going to be always finite. Okay, so you don't have to worry about it. You just take from t naught to infinity. That is what matters. So hence we write it like this. So I don't put any lower bound here. We just put it like this. Dt is finite. Is this clear? We just put it like this. We don't put any restriction. Okay, so let's look at the proof of that. Proof. So what is the theorem saying? The theorem saying that these are the two conditions. If the trace of AT is 0, or if the trace of AT, the limit, is going to minus infinity, then we are done. Okay? How do you prove something like that? So let's look at this. Let phi of t be the fundamental matrix of the system x prime equals to at times x. We start with this fundamental matrix. Is this okay? Now you see all solutions okay, of x prime equals to at times x is bounded. Okay, that will imply that the fundamental matrix is bounded. Okay, Okay, how is it, why is it true? Okay, if you are not convinced here, what I want you to do is please pause the video, think about it, why this is true. Okay, so let me tell you why this is true. See, maybe I will not put it here. Let me do it in the border boundary here. See, x prime equals to 80 times x. X0 equals to, let's say, EI. EI is the ith unit vector. Ith unit vector. Here, that has a solution. What is the solution here? The solution is given by xi of t, let's say. Okay. Now, what is x? X is nothing but x1 of t, xi of t, xn of t. Okay, sorry, not x, but phi, fundamental matrix phi. Now, all solutions of this system is bounded, right? So basically, if you take this initial data, right? So basically, if I am looking at a solution which passes through the ith unit vector at t equals to 0, that solution is also going to be bounded. So each component of this matrix, fundamental matrix phi, which is given by x1, x2, xn, is bounded. If each component is bounded, of course phi has to be bounded, right? This is trivial, right? This is trivial. So please check this part. I gave you everything. You just have to do some calculation. Nothing to do. It's basically every component is bounded. The matrix has to be bounded. Okay. So please do that part. Okay. So check it. Now you see what do we have is this. You remember the Abel's theorem, right? Yeah. So by Abel's theorem, you remember what we did using Abel's theorem? We showed that if it is linearly independent at one point, it has to be linearly independent everywhere, right? The set of matrices, vectors, right? We proved that part. So here also we are going to use Abel's theorem. Okay. By Abel's theorem, what you can say is this: if you take the fundamental matrix, the determinant of phi t, okay, is nothing but determinant of phi at the point 0 times exponential 0 to t trace of as ds. Is this okay? This is by Abel's theorem, right? Direct. And hence, what is phi inverse of t? It is nothing but adjoint of phi t by determinant of phi t. Here, adjoint of phi t by determinant of phi t, right? That's what phi inverse of t is. So you see, so this will be adjoint of phi t by determinant of phi t is given by determinant of phi 0. Why can we write it like this? See, phi is a fundamental matrix. Determinant of phi 0 is never going to be 0. Yeah, because phi is invertible, right? So determinant of phi 0 is non-zero, right? So an exponential is always going to be positive. So essentially this is not a problem. So exponential 0 to t race of as ds. Okay, this is there. Fine. Now you see this limit of trace of at is either greater than minus infinity or it is 0. So if this is the case, then exponential of this particular thing has to be bounded. Yeah, this has to be bounded, right? See, if this is 0, let's say, so it is basically adjoint of phi t by determinant of phi 0. Okay, and either or if it is minus infinity also, the trace of at, the integral of that is minus infinity also. Okay, so sorry, greater than minus infinity, sorry. Yeah, then also this is going to be bounded. So therefore, one can say that norm of phi inverse of t is bounded. Okay, so yeah, so you remember, so this part is fine. What we proved is this. See, if all solutions of the system x prime equals to 80 times x is bounded, yes, then all solutions, then the fundamental matrix is going to be bounded. Yes, of course, it means that the norm is bounded essentially. and norm of phi inverse is also bounded. Yes? Okay. Now, you see this equation, x prime equals to at times x plus b of t. Yeah, this equation, sorry, times x, right? This is the equation. So you can write it like this: at times x plus bt times x, right? This is what we can write it. Okay. Now this part, let us put it as b of small b of t. You remember we did the exact same thing in that when we did for the constant coefficient thing. We are also going to do this exact same thing. Okay. So let b of t is nothing but capital B of t times x of t. This is what we are defining. Okay. This is what we are defining. So each solution x of t such that x at the point 0 is x naught satisfies this equation, right? X of t equals to the solution of the homogeneous problem, phi of t, phi inverse of 0 x0. You remember, plus integral 0 to t, phi of t, phi inverse of s, b of s, ds. Okay. See, when it is a constant coefficient, okay, small remark. If it is a constant coefficient, what is phi of t? It is nothing but e to the power at, right? Then we can write it as e to the power 8. That is why we are writing e to the power 80 there for the constant coefficient. Here this is variable coefficient. We can't write it as e to the power 80, right? Okay, so I am not doing that. Okay, I hope this is clear. Now see, if one defines, if C is nothing but the maximum, clear, of supremum of t greater than equal t naught, norm of C of t, and supremum of t greater than equal, t greater than equal 0, let's just put it. It doesn't have to be t naught. It can be t naught also, but anyways, 0 greater than equal 0, phi inverse of t, right? So basically I am taking the supremum of phi, norm of phi, and supremum norm of phi inverse, and I am taking the maximum of those two. Let's just call that C. Yeah. Why? Because if we do that, then what do we have is norm of x of t. See here, I have this phi of t, phi inverse of s. This part is there. So I can take the maximums outside. You understand? This can be dominated by C. This can be dominated by C. This can be dominated by C. So I can take that out. That's what we are doing. So by triangle inequality, this is triangle inequality Ti. You can actually write it as C naught plus C naught is basically this particular thing, the boundary. I am just writing it to be C naught. Okay. So C naught plus C square 0 to t norm of b of s, okay, and norm of x of s ds. Right? That's what we are going to get, because small b is b times x, right? Yeah. Sorry, this has to be, I made a small mistake here. This is not capital B, this is small b. Okay. Now small b is capital B times capital X, so that is why I just wrote it like this. Is it okay? So now by Gronwall inequality, what do we have? We have the norm of x of t is dominated by C naught times exponential C square 0 to t norm of bs ds. Is this okay? See here I should write it. C naught is C times norm of phi inverse of 0 times x naught. Okay, this is what I wrote it as C naught. So normal will give us this. Clear? Is it okay? Now you see, we have assumed, since we have assumed that, you remember what is the assumption of b of s? It is the integral of b of s is finite. See? So if the integral is finite, therefore x of t is bounded. This is finite, exponential of a finite bounded term, so basically bounded. So x of t is bounded. So the next theorem which we are going to do will be in the same line, So essentially what we will do is this. So let the fundamental matrix phi of t of the system x prime equals to at times x be such that norm of phi t, phi inverse of t is less than equal some constant c. Okay, and this holds for 0 less than equal t less than equal, sorry, should I change? Maybe I should change it to t and s, t and s. Yeah, it is very easy to remember. I will tell you why. Because this part is nothing but that part, the inhomogeneous part of the Duhamel's principle. So that's why we remember this. So that's why. Okay. So please keep that in mind. Okay. And for now, okay. So what did I? Okay. This I was writing, right? So here I have to change it to s less than equal t less than infinity. Is this okay? This is the condition which I am taking, where c is a positive constant. Okay. Now further let the condition, okay, you that the other condition, so infinity norm of v bs ds, let's say that's finite, that condition which we used last class. So here this part, okay, is satisfied. This is true. Further let this is fine, is satisfied. Is satisfied. Okay. Then all solutions of x prime equals to at plus bt times x are bounded in 0 infinity. Here bounded in 0 infinity. And what is the condition provided? No, what am I doing? I wrote the condition. Sorry, I wrote the condition. Then all solutions are bounded in 0 infinity. Okay. This is the condition on the fundamental matrix, and of course the integrability of BS is required. Summability, that is there. Moreover, you can say much more here. Moreover, if all solutions of x prime equals to at times x tends to 0 as t tends to infinity. Clear? Okay. Then all solutions of x prime, this system, I have to write it all the time, at times bt times x, the part of system, clear, tends to 0. 0 as t tends to infinity. So you do realize what I'm trying to say. Exactly the same sort of theorems which we did in the other videos also. So here it is saying that you just need that condition on the fundamental matrix, that fundamental matrix phi t and phi inverse of you take both of them together, the norm has to be finite. And of course the summability. So this is basically, this is summability of B of S. This is finite. So it is summable basically. That is required. Once that is there, then all solutions, so it will mimic the solution. The perturbation is not a big problem, so it will mimic the solution. So essentially, if the solutions of the homogeneous, the homogeneous problem, if there's let's say bounded, okay, then the solutions of the perturbed systems are bounded. If they goes to 0, then the solution goes to 0. Okay, which is like a very, very straightforward thing. It just mimics that solution. Okay, let's look at the proof. The proof is not very difficult. Yes. One second. The proof. Okay. So what do we have? See, this part is already there, right? That part is already there. I can do the exact same thing, basically the same system. So exactly I can go on doing this because I did not use anything else. You see, this condition, the trace condition, where is it? See, this condition, so basically what I'm trying to say is this. Where is that condition? What did I write it? Okay. Oh, where is it? One second. I wrote it in something from, no? Where's the condition? Okay. Yeah, here. So since you see, phi t, phi inverse of S, that is given to be bounded, right? Okay. So you can use this condition, okay, in this part, right? So you see, x of t, we know we have x of t is nothing but phi of t, phi inverse of 0, x0 plus 0 to t, phi of t, phi inverse of 0, b of s, v x of s. I think I'm writing. Yeah, it's fine. Yeah, this is okay. So this is all satisfied, right? You remember? You see, this is the thing which we did earlier. Where is that thing? I wrote someone. Here. Okay. So this is the thing, right? The x will satisfy this equation. Yes. Okay. So you see, what I am going to do is this. Now, since in the earlier proof, what we did is we did it independently. You see, we proved that norm of psi inverse of t and norm of psi t is bounded. That's what we did. Clear? Okay. And then you take the maximum of those two and then you dominate it. That's what we did. Here we are doing it a little bit differently. See, all solutions of the homogeneous problems are bounded. The norm of phi of t is going to be bounded. That's given. That it has to be true. This is exactly the same thing what we did earlier. And this is given to be bounded. Phi t and phi inverse of 0 is given to be bounded, right? So you see that, so essentially you see, let's say this bound is given by C or whatever. So you see, therefore what we have is this norm of x of t is dominated by C times norm of x naught, right? So this is C, phi t, phi inverse of 0. See, phi t, phi inverse of 0. Where is it? Phi t, phi inverse of 0. This is for all s, right? S doesn't have to, s can be 0 also. You see? Okay. So this is bounded, right? So I will take it to be norm of x naught plus C times, okay, 0 to t. The norm of this is gone. Norm of Bs x of s ds. Okay. Now you use your Gronwall. So therefore, Gronwall inequality implies that norm of x of t is bounded by c times x naught, okay, exponential of c 0 to infinity norm of bs ds, okay, and which is basically bounded. That is given, right? That is given. Yeah. So it is very, very trivial. Once you write this part, in the other part, what we did individually, we showed that the fundamental matrix and the inverse of the fundamental matrix norms are bounded. Here, it is given to be phi t times phi inverse of 0 is given to be bounded. So we just use that bound. Nothing doing here. Here. So it's very trivial. I mean, it's not very difficult actually. Okay. Now, again, the second part. What is the second part? So this part is also very easy. I'm not going to do it in the whole, but I will just give you an idea of how to do it. See, it is given this fundamental, the system, all the solutions are going to 0 as t tends to infinity. And we have to show that the part of system also exactly mimics the same sort of, properties. Okay. So how do you do it? So see, now, again, so this is part 2. Again, x of t, yeah, is phi of t, phi inverse of 0, clear, x0 plus 0 to t, phi of t, phi inverse of 0, b of s. I'm making some mistake somewhere, no? One second, I'm making some mistake somewhere. Formula, yeah, this is phi inverse of s. I should not write phi inverse of 0. So I'm sorry about it. But anyways, it does not change anything, but the formula is correct. This is the formula. Here it is phi inverse of 0. Here it is phi inverse of s. Okay, and here also, sorry, phi inverse of s, b of s, ds. Clear? Now this is fine. And x of s, d of s. Is it okay? And so basically what we are going to do it is, I am going to do it from 0 to t 0 plus, I will just break it up, t 0 to infinity, phi of t, phi inverse of s, b of s, x of s, ds. Is this okay? This we can write it. Now, therefore, if we take the norm on both sides, it is x of t. Okay, if we take norm on both sides, that is given by norm of phi of t, phi inverse of 0, norm of x naught, right? That's what we're going to get, plus norm of phi of t. I can take that out, right? And then 0 to t naught, phi inverse of s, b of s, x of s, ds. Okay, plus c times this, let's call this as m, this term, let's just call that part, that term as m, You understand this c times, so basically c times norm x naught exponential, this particular thing, I will just call that as m. Is this okay? So say m times t naught to infinity norm of b s ds. Okay, I will just write that part like this. Clear? So x of t is given like this. Okay, now let's say let epsilon greater than 0 be given, small enough. Okay, again, this part of the theorem, I am not doing it explicitly. I am not doing every single line. What I want you to do is, please check it yourself. This is very easy actually, but I am still doing it. But I will leave some gaps. I want you to fill those gaps up. Now, see, the thing is, if you look at this particular B of S, right? What is the condition on B of S? I wrote somewhere, no? The integral of B of S is finite, I think. That's what I wrote. Huh? This one is finite, given. Yeah? I hope this is okay, right? See, this part is there, no? Where is it? Yeah. This is finite, integral. So basically, BS is summable. Since BS is summable, this particular thing, T naught to infinity, norm of BS ds can be made less than equal epsilon, right? So in that case, T naught to infinity, norm of BS ds can be made less than equal epsilon by 2. For sufficiently large T naught, let's say, for sufficiently large T naught. Large T naught. You see, this is why T naught here, why when I wrote, I did not write what T naught is. T naught will be chosen later. So now we have chosen later. Okay, you see, now we chose T naught sufficiently large such that this is happening. Clear? Okay. Now see that also, if all solutions of x prime equals to 80 times x goes to 0 as t tends to infinity, then this is trivial, right? Norm of phi t goes to 0 as t tends to infinity. Why? You remember x1, x2, x3, what is phi t consist of? x1, x2, xn, right? And each x1, x2, xn has to go to 0 because all solutions are going to 0. x1, x2, xn, those are solutions. So they have to go to 0, right? So if they go to 0, then the norm, you can show that the norm will also go to 0. Okay. So please check this part again. Check this part. Not very difficult, very, very easy, but you can do it. Please do that part. Okay. So if that goes to 0, therefore, see, what we can say is the first two terms, okay, this term and this term, the sum of those two terms, okay, can be made arbitrarily small, right, by choosing t large, right? See, norm of phi t goes to 0, right? So this goes to 0, this goes to 0. Yes. So what we can say is essentially, and this is a bounded quantity. This is a bounded quantity. Okay. So what we can say is we can take this part and this part. The sum of that, I can make it less than epsilon by 2. That's what we are saying. Okay. So I will just write it. The sum of first two parts. Sum of first two. I am not going to write the whole expression. First two terms can be made less than epsilon by 2 for large enough t. Is this okay? Okay. And so therefore what we have is this is less than, this two part is less than epsilon by 2. This is given to be less than epsilon by 2. So if you add it up, then this is going to be, therefore norm of x of t is finite for large t. Yeah. So hence that will imply that x of t goes to 0 as t tends to infinity. Done. Okay. Done. Very, very simple. It's not very difficult theorem to prove. Okay. So we are going to end this video, but before we do that, I will just give you one theorem. I want you guys to do this theorem yourself. Okay. Very, very important, but extremely easy theorem. The theorem. So up till now we were talking about part-up system. What about the inhomogeneous system? Okay. So the thing is this. Suppose I will write down the theorems. You have to prove it yourself. Very, very easy. Again, you can do it. Suppose every solution of the differential system x prime equals to 80 times x. Yeah, is bounded in 0 infinity. Okay, again, why 0 infinity? Because we are looking for as t tends to infinity, so we don't care about what happens at negative time. Then every solution of the system, I think you can guess what is going to happen. X prime equals to at times x plus bt, okay, are bounded. Can you think of any condition under which this will be bounded? Okay, provided, and this is a very simple condition, at least, okay, one of its solution is bounded. Solution is bounded. Okay, I hope this is clear. See, I will just give you the proof. I will not write the proof down, but it is trivial. See, any solution of this inhomogeneous equation, what is it? It is the solution of the homogeneous problem, and then the one solution of the inhomogeneous problem. You know that at least one solution of the inhomogeneous problem is bounded, right? So that part is taken care of. What about the part for the homogeneous problem? You know that all solutions of the homogeneous problem are bounded. So the fundamental matrix is bounded, and hence everything is bounded. Okay, so this is trivial. But anyways, write it down. Huh? And there is another theorem which you can say, and this is theorem 1, theorem 2. Theorem 2. Again, this I will not prove extremely, it is trivial. Huh? You guys can do it yourself, so you can do it. So let's say, suppose every solution of x prime equals to 80 times x, okay, is bounded. Same sort of thing, huh? In 0 infinity. Same sort of theorem. And you need a different condition. Okay, what is the condition you need? That I wrote the condition somewhere, right? Where is it? Where did I write it? The trace thing, huh? Where is that trace thing? I wrote that condition, huh? 1 second, huh? The trace condition I wrote somewhere. This one. So let's just put that condition a star. This is a trace condition, huh? And the star is satisfied. And star is satisfied. Okay, then all solutions of the homogeneous problem, solutions of x prime equals to 80 times x plus b of t is bounded. You need a extra condition, provided norm of BS is summable, huh? Summable. Yes. What we did up till now, if you have understood all the proofs, this is trivial. Okay. So again, theorem 1 check, theorem 2 check. So check both the proofs. Clear? So with this, I am going to end this video.